Hi, welcome back to AP Physics C Mechanics. This is topic 6.5. This is called rolling, specifically rolling without slipping. And this is very important because it allows us to use some of those equations or relationships that we established in Unit 5 for tires, okay, or situations where the object is rolling. So one thing to note, total kinetic energy system is now the sum of a system's translational and kinetic energies, right? When an object is rotating and moving linearly, to find the total kinetic energy, you will just simply add up the translational and rotational kinetic energies. While rolling without slipping, the translational motion of a system center of mass is related to the rotational motion of the system using those equations that we already kind of established, right? Where the displacement of the center of mass is just simply r theta. The speed of the center of mass is r omega, and then the acceleration of the center of mass is simply r alpha, right? Those are stuff that we talked about way back there in Unit 5. And one thing to note is that rolling without slipping will apply that the frictional force does not dissipate any energy from the system. And so what really keeps an object rolling without slipping is when the static friction holds true. And this is the result, right? This little diagram here is the result of combining those rotational motions, okay, with the linear motion. And what you actually see is at the point of contact with the ground, the object is not moving, but the center of mass, which would be the center of the wheel, is moving, and then the top is actually going 2 times that speed. And it comes from the what you see here, the combinations of the rotation and the translation, what they call pure rotation and pure translation. If an object is rolling, if it is slipping, that means there's kinetic friction involved. Rolling without and slipping, right? The idea is static friction is the friction that is what's holding things or causing this to happen. But if there is slipping, then there's kinetic friction involved. But then eventually what happens is the kinetic friction will dissipate energy, but then it begins to roll without slipping. Think about a bowling ball. When you first release the ball down the lane, it kind of slips a little bit and then it begins to roll. Okay, that's what we're talking about when we say rolling with slipping. All right, so let's look at an example problem. Okay, so here we have a sphere of mass m, radius r, rotational inertia I, released from the rest at the top of an inclined plane of h, shown below. If the plane has friction so that the sphere rolls without slipping, what is the speed v sub cm of the center of mass at the bottom of the incline? Okay, so this is a very common question that you do see kind of running around in these scenarios. Okay, here the good thing is though they only say I. But you can also note that if they will want anything other than, right, I in your answer, this is simply 2/5 mr squared as a rotational inertia. And we're actually going to apply that here. And so what happens is, this is a conservation of energy problem. So we know that the change in energy of a system is equal to 0. And that means our K before, or initial, let's call it initial, not before. All right, so K initial plus U initial equals K after or final plus U final. And remember, K is going to be K translational plus K rotational. Okay, bottom of the incline 0, hasn't started moving yet linearly or rotationally, so that is 0. So we get our typical U sub I is equal to K sub F. And so U sub I is mgh. K sub F is going to be K translational plus K rotational. So we end up with mgh equals 1/2 mv squared plus 1/2 I omega squared. And we know because it says without slipping, omega or V equals R omega, where omega is V divided by R. So we just plug all this information in and solve. So we get mgh equals 1/2 mv squared plus 1/2 2/5 mr squared times V over R squared. Okay, and so just to save a little space, this will become V squared over R, V squared over R squared, and we can do some canceling. So cancel the R squares. All these masses cancel out. This 2 cancels that 2. And so you end up with GH equals 1/2 V squared plus 1/5 V squared. So note that you can write I omega 1/2 I omega squared in terms of V squared, okay, or in terms of linear quantities, okay. So now we just have to add 1/2 and 1/5. That's going to be 7/10. So we say GH equals 7/10 V squared. And now we just solve it for V. Okay, so you're going to end up with 10 over 7 GH square root, and that will be the speed of this sphere at the bottom of the incline. All right, so we have one more video left to do. We're going to talk about what happens when we look at orbiting satellites around central objects.